Hello. Today our topic is colligative properties. Colligative properties actually is you can say it is a democratic property. In a democracy, what happens? How do we elect government? By voting. Each and every one we give a vote, and the one who gets the majority wins. In case of colligative properties, the similar thing is happening. Colligative properties. An example is osmotic pressure. We can say osmotic pressure is a colligative property. Elevation of boiling point is a colligative property. Depression of freezing point is a colligative property. Along with that, lowering of vapor pressure, relative lowering of vapor pressure is a colligative property. All of this occurs because there is a solvent in which some solute are mixed. Now, two types of solutes are present. One type will be volatile solutes and the other type will be non-volatile solutes. So we will divide solutes into two categories. So what are the categories? One is volatile solutes, and the other is non-volatile solutes. So we have divided them into two categories. Suppose we are making a solution of a liquid and a volatile solute. And we are making a solution of a liquid with a non-volatile solutes. Now, what are volatile? Volatile compounds or volatile solutes are those solutes which have very low boiling point. Room temperature, they will vaporize, they will expand. That means from the liquid state, they will go to the gaseous state, will expand in volume. Non-volatile solution, on the other hand, does not actually expand in volume. They are solid. You cannot compress them with pressure. So, non-volatile solutes are those which are solid in nature and that does not vaporize in room temperature. That means camphor will not be treated as a non-volatile solid. This solid, but it vaporizes at room temperature, so it will be regarded as a volatile solid. Okay. Now, let us break it down to several factors. In the first factor, we will learn about the vapor pressure. Have you ever considered that? Have you ever thought that how the clothes that we go for washing, that we put in washing in a washing machine, or we wash it with our hands, they got all wet, they get all wet, and we just squeeze the water out and we keep it outside the house or in the roof. After some time, in about 1 or 2 hours, the fabric, the cloth gets all dried up. Now we all know that for water to get vaporized, it takes 100 degrees Celsius. But do you think that the outside temperature has reached 100 degrees Celsius and all the water in the cloth has vaporized? I guess not. So there is a very big difference between evaporation and drying. There is a big difference between evaporation and drying. What is evaporation? It is the phenomena in which the liquid is transferred from its aqueous state or the liquid state to the gaseous state. The substance is transferred from its liquid state to the gaseous state. That is evaporation. And what is drying? Drying means the object which was wet now does not have any water molecules inside it or any liquid molecules inside. You can dry a cloth. Even drying is referred to as, most of the cases, 99.9% of the cases, drying is referred to as something which is soaked in water, which has water content inside it, is wet, and the one which does not have any water content inside it is known as dry. Even solvents, suppose you are using for a reaction. We have discussed about reactions like SN1, SN2 reactions. There we have used ethanol, alcoholic medium. If the alcohol is completely dry, means if the alcohol is completely devoid of water, absolute alcohol then we will say that it is a dry alcohol. Same goes for other solvents like DCM, dichloromethane, trichloromethane, CHCl3, and even hexane, ethyl acetates. These are the solvents which are used in organic reactions. Diethyl ether, a very important reagent, solvent when we do perform the reaction of Grignard reagent. So these have to be completely dry. That means these have to be devoid of water. Now let us come back to our question that our cloth, which is soaked in water and put outside for drying, is what is the phenomena that is happening? How the drying process is taking place outside our room. Even inside, if you just keep it there, after a few hours, you will see that it has become dry. It might take longer time than outside, but eventually it will dry off. Now, the question is why it is drying. The answer lies to the concept of vapor pressure. Lies to the concept of vapor pressure. If you open your deep fridge, you have a fridge in your house, you open the deep fridge, and you will find that some of the vapors is coming up. These vapors are actually the vapors of the liquid, or you can say the vapor of water that is present inside that deep freeze. Okay. So at every temperature, every substance has a vapor. Every substance, if it is liquid in nature, if it is solid in nature, for the substances which are solid in nature, this vapor quantity is very, very less, means negligible. But for liquid, it is appreciable, means it is what you can count. So vapor pressure is defined as the pressure exerted by, who will exert? Exerted by the vapors of the solvent. Okay, vapors of the solvent, or you can say the liquid, vapors of the solvent or the liquid. Pressure exerted by the vapors of the solvent or the liquid on the liquid or solvent itself. Okay. On the solvent or liquid when they are in equilibrium with each other, when they are in equilibrium. Okay. When they are in equilibrium. What does this mean? This means that suppose this is a bowl. Okay. And it has water inside it. So at any temperature, this from here, there will be certain vapors which will be coming out from the surface of the liquid. And these vapors will exert pressure on the surface of these liquids or solvents. This pressure is known as the vapor pressure of the solvent or liquid on the solvent itself. Now, it is, suppose the pressure here is 0.1 atmospheric pressure at room temperature. 0.1 atmospheric pressure of the vapors that comes out from the surface of the liquid. So when the liquid vapors comes out from the surface of the liquid, it exerts pressure and it is very less at room temperature. Suppose it is very less at room temperature. Now, as it is less at room temperature, so what will you do? You will increase temperature. Suppose you are heating this with the help of a Bunsen burner. Okay, suppose you are heating this with the help of a Bunsen burner. Okay, and this is a gas line. This is a dish. This is a stand on which you are keeping it. You are heating it. Now, the temperature at which the vapor pressure of the liquid or solvent reaches atmospheric pressure. Okay, the temperature at which the vapor pressure of the liquid or solvent reaches the atmospheric pressure will be known as the boiling point. Be known as the boiling point of the liquid or solvent. Okay, so the temperature at which the liquid or solvent reaches the atmospheric pressure will be known as the boiling point of the liquid or solvent. This is what vapor pressure and boiling point has in relation. Now, we have discussed about the vapor pressure. Now we will discuss about the lowering of vapor pressure. Now, vapor pressure depends upon three major things. Vapor pressure depends on, what are the factors on which vapor pressure depends? First one is, as we have just seen, temperature. Temperature is one of the important factor. It increases with increase in temperature. Okay, vapor pressure is directly proportional to temperature. Now, what will be the second? Nature of the solvent. Nature of the solvent means, is it a high boiling liquid or is it a low boiling liquid? What is it? Okay, nature of the solvent is very important. Now, low boiling point liquids or lower boiling liquids will have a higher vapor pressure and vice versa. Okay, so solvents or liquids with lower boiling point will have a higher vapor pressure at a particular temperature than a high boiling liquid. Okay, so from here, what type of question can you expect? The one type of question that you can expect is comparison of methanol and water. Okay, so methanol and water. Between methanol and water, we know that methanol is an alcohol. It has a lower boiling point than water. So at room temperature, vapor pressure of methanol will be higher than that of water. At room temperature, the vapor pressure of methanol will be higher than that of water. Okay, because methanol is a lower boiling liquid and water is a higher boiling liquid when you're comparing them. But if in place of methanol, if you're having aldehyde, then it will have a more vapor pressure. If you have ketone, the vapor pressure will rise accordingly. If it is hexane, then also it will be rising. So this is, you have to keep in mind. Okay, solvent that we are using, how much lower the volume or boiling point will it reach? Okay, the third one. Third one will be addition of solutes. Okay, addition of solutes. So two types of solutes we have discussed right now. The first type, volatile solutes. Second type, non-volatile solutes. So what is the basic difference we have discussed? Now, here we will discuss about the solutes which are both. Okay, means, the solutes which are non-volatile in nature. Because volatile solutes, if mixed in liquids, then we will see about this. This will be known as a dissolution of gases in liquids. Okay, dissolution of gases in liquids, and that has already been explained in Henry's law. I will share the video with you again. Okay, so right now we will be focusing on the thing in hand, that is addition of solute, which is a non-volatile solute. Okay, this is a non-volatile solute. Non-volatile solutes. What happens when you're dissolving a non-volatile solutes to a solvent? Okay, or you're making a solution. This solution, now, suppose you're dissolving NaCl in water. You're dissolving NaCl, or putting pinch of NaCl in water, and the water will get dissolved. Oh, sorry, the NaCl will get dissolved in water. What does the water do? The water will tear the NaCl apart. The water, what will it do? It will tear the NaCl apart. Okay. Now, NaCl has electrostatic force of attraction. Water has a hydration force. NaCl has a electrostatic force of attraction. Water has a hydration force. Okay, hydration energy. Now, the hydration energy of water is sufficient to break the bonds of Na and Cl. Okay, Na plus and Cl means hydration energy is enough to break the bond, electrostatic bond between Na and Cl. Water, the hydration energy of water is actually capable of breaking the almost 99.9% of the salts from sodium, potassium, and ammonium. Okay, 99.9% of the salts made from these ions are easily broken by the hydration energy of water. Now, there is a reason behind it, but right now we will not going to discuss on that. Let us focus on here. Water separates Na and Cl from each other. It is breaking their electrostatic force of attraction. Na, now Na plus is being captured by the lone pairs of oxygen in water molecule, and the Cl minus is captured by the delta positively charged hydrogen of the water molecules. But they are being stagnant, or they are being piled up between water layers. They are being piled up between water layers. Now, you will see that there are bilayer. Now, you will see there is a concept of bilayer. So this bilayer is, if this bilayer is strong enough, then we will see a certain type of vapor pressure. If the bilayer is weak, then we will see a different type of rising or falling of vapor pressure. Okay. Now, if solvent solute bonding is stronger than solute and solvent bonding, then we will see, or we will observe, a lowering of vapor pressure. A lowering of vapor pressure. Now, the question is why? Why we are witnessing that? Witnessing this phenomena? Because now it was solvent. There is a certain force of attraction. Now, between these two layers, a solute layer has entered. Now, the solute layer has a stronger force of attraction between it and solvent. Okay. Now, the one who is at the surface, the molecules which are at the surface of water, what will they face? They will think that they will face a stronger force of attraction towards their core. That means the second layer between the second layer, which is the solute layer, will hold the surface solvent molecules strongly. Okay, and that will release fewer amount of solvent molecules to the atmosphere or just above it. So fewer molecules will exert fewer pressure. That is why you will observe a lowering of vapor pressure. So what we have seen at first, if 100 molecules of solvent would have gone up and exerted the pressure, after adding the non-volatile solute, the number would have decreased to 50 or 40 like that. Okay, so if it is halved also, then the vapor pressure will get halved. If it became 1/4, then it will become, the vapor pressure will also become 1/4. It all depends on the how strong the bond between the solvent layer and solute layer is. Accordingly, we will see that they will make certain type of solutions. One will be maximum boiling solutions and the other will be minimum boiling solutions. Okay, maximum boiling solution means the temperature would be required, maximum amount of temperature, high temperatures required to boil off that solvent mixture, solute solvent mixture, and lower amount of heat is required to actually heat or bring the solution to a boiling. Okay, that is known as minimum boiling mixtures. Okay, now these two are being separately classified as azeotropes for liquid mixtures. Okay, and that also I will give you. Okay, in another video it is there and I will give it to you. So this is the main thing. So this is known as lowering of vapor pressure. Now we will say that vapor pressure of pure solvent, accordingly we can conclude that vapor pressure of pure solvent is greater than vapor pressure of solution. So this is P0, it can be considered, and this can be considered P. So P0 is always greater than P. Okay. Now, this P0 and P, the decreasing vapor pressure of a solvent by addition of non-volatile solute is lowering of vapor pressure, but we will not stick to the lowering of vapor pressure. We will go beyond. We will go for Raoult's law for non-volatile solutes in liquid system. This is known as relative lowering of vapor pressure. This will be known as relative lowering of vapor pressure. Relative lowering of vapor pressure. Relative lowering of vapor pressure. Okay. Relative lowering of what does it means? That means this is the lowering of vapor pressure, and if you divide it with the original vapor pressure, then you will get the relative lowering of how much in relation it is decreasing. Now this whole thing will be equal to the mole fraction of solute because it is directly dependent on the solute. So P0 minus P by P0 will be X of solute. Okay. So X of solute means W of, let it be XB. Okay. B means solute. So WB by MB. Okay. Number of moles of solute divided by total number of moles. Okay. This is mole fraction. This is known as mole fraction. So this is number of moles of solute divided by number of moles of solvent plus number of moles of solute. Understood? Clear? Now, if you are making a very dilute solution, if suppose we are making this a very dilute solution, for a dilute solution, number of moles of solvent will be greater than number of moles of solute. Okay, this is actually N of solute and this is N of solvent. Okay. So what can you say? That it will be P0 minus P by P0 relative lowering equals to NB by NA, or you can simply write WB by MB by WA by MB, or WB by MB into MA by WA. Okay, anything you can write. Understood? So we have to abide by these things. Okay. So now we will go for the Raoult's law for liquid mixture. Okay. According to Raoult's law of liquid mixture. So Raoult's law of liquid mixture, what does it say? It says the partial pressure of A will be the mole fraction of A into the, this is the absolute, means the original vapor pressure of pure solvent A. and PB will be equals to XB times P0B. Pn and PB, these are known as partial vapor pressures or simply partial pressures, and this XA and XB are mole fraction of A and mole fraction of B, and P0 A and P0B are, these are vapor pressure of pure solvents A and B. Okay, this is the Raoult's law for liquid-liquid mixture. Now, all of this we have studied, and that is why we can say that colligative property, we can summarize colligative property as a solution which depends on colligative property. A colligative property is, or colligative of a solution, you can say, of a solution, colligative property of a solution which depends upon the number of particles, which depends upon the number of particles, which depend upon the number of particles present in solution, number of particles present in solution, okay, but does not depend on the chemical nature of the solute, but does not depend on the chemical nature of the solute. Okay, it does not depend on the chemical nature of the solute. So this is the main thing. It depends on the, that is why at first I have told you that it is like a democratic property. Who is voting does not matter. How many people are voting, that matters. Okay, it can be anyone. A person who is a teacher, he is also voting. A person who is a student at that time is also voting. The person who is a cricketer, who is a footballer, who is associated with any other work is also voting. So it is all the people, means number of particles, number of peoples who are voting, and it does not depend on the quality and what type of people are voting actually. It does not depend on that. Okay, so this is our total format. Now the rest of the colligative properties, which are elevation of boiling point, depression of freezing point, osmotic property, along with abnormal colligative properties, we will discuss in our next class.